So the problem we are trying to solve is to find the length of the longest path in the DAG. So how do we do this in general? Sorry, for any generic DAG, how do we find the length of the longest path? So let's zoom in on some node. Let's say we have some node V. Okay. Now, let's say it has its predecessor nodes. Right? The incoming, it has, let's say it has somewhere these three nodes in the DAG. They have edges to V, going from them to V. Right? So let's say these three nodes, let's call them U1, U2, U3. They have edges going from them to V, and no other vertex has an edge going from it to V. Okay, so the in degree of V is 3. Okay, so let's assume there's nothing special about 3, but let's assume this is the case. All right, so now let's focus on the length of the longest path that ends at V. Okay, length of the longest path that ends at V. Okay. Well, let's focus on the longest path. Okay, that ends at V. Okay, so what are the possibilities? It's possible that the path starts from some node in the DAG and it goes to U1, right? And then the final edge in the path is this. Okay. It could be that the length of the longest path that ends in V looks something like this. First, there's some path which comes to U1, and then the final edge in the path is this. Okay. Or it could be that the path looks something like this. It starts from some node, it goes up to U2, and then this is the final edge in the path. Or it could be that we have some node. Well, this node could be one of the previous could be one other node. Could even be one of these two nodes, but let's say we just draw it this way, and there's some path from it to U3, and then the final edge in the longest path is this. Right? So remember, we're looking at the longest path that ends at the node V. And for that path, these are the only three possibilities in this case, right? There is no other possibility because any path that ends at V has to come in from one of these three edges. Okay, so the longest path also has to end with one of these three edges. We do not know which of these three edges it ends. It could be either of them, right? So there are these three, there are these three possibilities. Now, supposing, let's say this one was the longest path. Okay, let's say this was the longest path that ends in node V. What can you then say about this path? Well, if you look clearly, if you look carefully, you can say that this path has to be the longest path that ends in node U1. Right? Why is that? Well, clearly it has to be the case because if that was not the case, you could, if there was some other longer path that ends in u1, if this path was longer than this, then you would simply take this path, the longer path, and add one more edge to it to get an even longer path that ends at v, right? Now that would be a contradiction because we assume we are saying that this, supposing this was the longest path that ends in v. Okay, so clearly something like this cannot happen, right? So what we are saying is then that if this is the longest path that ends in V, if we remove the last edge in that path, what we are left with here, this has to be the longest path that ends in U1. Okay, so there is some sort of recurrence relation, recursive relation that we are building here. Okay, and that is always the first step in dynamic programming, to try and solve a problem recursively. Okay, so to do this now, let's we can define this term. Let's define this term L of V to be the length of the longest path. It's the length of the longest path that ends in node V. And basically what we have said here is L of V, this is basically the maximum of the length of the longest path that ends in U1 plus 1, right? And the length of the longest path that ends in U2 plus 1, and the length of the longest path that ends in U3 plus 1, right? Do you agree? The longest path, the last edge in the longest path has to be either this or this or this, right? There are three possibilities in this case, and we do not know which one of them is. So we have to check all the three possibilities and we pick the maximum one out of them. Okay. So if you want to write this a little more precisely, we would say something like L of V, sorry, let's say L of V is the maximum of this quantity L of U plus 1, where U comma V is an edge in the graph, right? Or in other words, for all U which are predecessors of V, right, is an edge from U to V, directed edge from U to V. We compute this term L of U, and the maximum of all these L of U's, we add a 1 to it, and that is our L of V. Okay. So given this, so this is really the key, right? Coming up with something like this is really the key first step in dynamic programming, right? Finding a recursive solution, right? For the optimal solution, trying to find a recursive formulation. And that is really the key part in dynamic programming, the first key step. Because once we have this now, we can directly write a recursive program, right? So our pseudocode would look something like this. Maybe we would have, let's call it L path to compute the longest path that ends at a given node V. We could maybe have some, we would have some variable max that we would say initialize the length, longest length to 0. And then we would say simply for all U which are predecessors of the node V, we would simply check if L path, so recursively, L path of U plus 1 is greater than the current max. And if that is the case, we simply update the current max to L path plus U, L path of U plus 1. And we do this for all the predecessors. And at the end, we simply return the maximum length that we have found. Okay, this is a direct translation of this recursive definition, right? We're exactly taking what this definition is saying and writing a pseudocode for it. All right. Okay, is our problem solved? Well, almost. Is this correct? Well, it's almost correct because there's a small detail missing, is that um, if we come back to this picture, we recall that our problem was to find the length of the longest path in the DAG, right? So given the entire DAG, what is the length of the longest path? And what we have computed in L path is the length of the longest path ending at some node V. All right. So to find this length of the longest path in the entire DAG, we basically have to we'll have to iteratively check for all the nodes in the graph what is the length of the longest path that ends at that particular node, right? So we go one by one after we compute L path V for all the nodes, and then we check for each of the nodes what is the value of L path of that node. And the node which has the highest would correspond to the length of the longest path in the DAG, right? So to do that, we might have something like this. We would have the final result answer initialized to 0, and for all the vertices V in the set of vertices capital V, we would just check if this variable is less than L path of V, right? L path of V is computed by this code, and if answer is less than L path of V, you simply update your answer to L path V. Right? So answer will store the length of the longest path that ends at a given node V. And you do this for all the vertices V, sorry, you do this for all the vertices V in your graph. And what you will finally be left with is the value of answer would be the length of the longest path in the DAG. Okay, so this solves the problem. Okay, so are we done? Well, not at all, actually. So I let you convince yourself that the runtime of this code is really terrible in the worst case, right? So it's worse from you. It's even worse than our Fibonacci example. So we try and write out a recurrence relation and convince yourself that this code can be, the way it is written, just simply like this, can be terribly inefficient, definitely exponential. So how can we do better?